Hi. Today we're going to start off our look at thermal physics with a look at some basic thermal concepts. Thermal physics is very much the study of particles and energy. Obviously there's forces involved as well, but we're going to look at the structure of matter and how transferring energy to and from objects affects that structure. So we're going to have to start with a look at what is the basic structure of matter. And let's give it a bit of a historical context. We'll start with the idea of the atoms in right from ancient Greek times through to current evidence for atoms, or more recent evidence for atoms. We'll introduce a modern model of an atom, not in great detail, that'll come in a later unit, but we will look at a modern model. We'll look at how atoms are affected by energy, and we'll look at the mass of atoms and the mass of substances and how those two things are related. And we start in ancient Greece. On the left, we have Heraclitus. On the right, Parmenides. I may be pronouncing that completely wrong. But the important point is that Heraclitus believed in the nature of change. He said that everything is change. The nature of existence is change. Parmenides or Parmenides said that all change is an illusion, an idea called monism in philosophy. So Heraclitus said that everything changes, and Parmenides says that everything stays the same and change is an illusion. Parmenides' idea is a very strange idea to us, but it's not quite as strange as it seems at first, because he wanted to know what was the mechanism, what was the process by which a fire burns wood and turns into smoke and ash. And the resolution to this problem, or a proposed resolution to this problem, was the ideas of Lepidus and his student or pupil, Democritus. Democritus said, well, here's the idea. In reality, everything stays the same because there exist these things called atoms. And everything is made up of tiny atoms. And these tiny atoms cannot be divided, they cannot be moved around. Okay? But they can be combined. The idea was that of the atoms and the void, which was just a kind of fancy way of saying vacuum, really. So nature consists of atoms and the void, according to Democritus. The atoms are indestructible and immutable. They cannot be changed, they cannot be destroyed, but they can get together. And then they get together, when they cluster together, that gives rise to macroscopic properties. And when we split them apart, it changes those properties. So in wood, there were atoms of smoke and atoms of ash and atoms of water and atoms of air. And when you burn wood, and atoms of flame and atoms of heat, because things like flames and heat, which we wouldn't consider to be made from atoms to us, to Democritus, were made from atoms. And by setting fire to wood, you would release all those atoms and they would give rise to the change. So we appear to see change, as in Heraclitus, but really nothing is changing, as in Parmenides. It's just a matter of rearranging atoms. So that was Democritus's idea of atoms. Now, Democritus and Heraclitus and Parmenides all belong to a class of philosophers known as the pre-Socratics. They came before the three great Greek philosophers, Socrates, Plato, and Aristotle. And we only know about them because of the writings of, well, this man, Aristotle. Aristotle wrote about Democritus, and he wrote about atomic or particle theory. But he actually wrote about it in order to disagree with it. Aristotle instead said that there were four elements: earth, air, fire, and water, and that these four elements in different mixtures formed all of the substances that we could see, and that you could take these substances and subdivide them. So a log might be 60% earth, 20% fire, and 20% water, for example. But no matter how much of a log, until you had the smallest piece of possible microscopic log, it would still have 60% earth, 20% fire, and 20% water. A very different idea to the atomic idea. So Aristotle wrote about atomism, wrote about the atomic theory, but only in order to disagree with it. However, over the centuries, evidence built up that Aristotle was not in fact correct and that the atomic idea was a much better model. Well, what was this evidence? Cheese. Yes, I remember cheese. So cheese, the idea is, according to Aristotle, cheese is formed up from atoms of earth, air, fire, and water, and you can have the tiniest little bit of cheese and it still have those earth, air, fire, and water. Democritus would have said, no, it's atoms of, well, I'm not quite sure, maybe atoms of cheese itself, or atoms of milk and atoms of earth, or whatever. But you could subdivide it, but eventually you would get to individual atoms. So atomic theory and Aristotelian theory, two different things. Now, evidence for the existence of atoms, or support at least for the existence of atoms, comes from the nature of solids, liquids, and gases. How can we describe solids, liquids, and gases? Well, we can describe them in terms of their shape and in terms of their volume. Solids have a fixed shape and a fixed volume. Liquids have a variable shape and a fixed volume. Gases have a variable shape and a variable volume. Gases and liquids, the two things with variable shape, we can give the name of fluids. Okay, so solids and then fluids, or solids, liquids, and gases. But how does particle or atomic theory help explain these properties? Well, in a solid, the atoms are fixed in place. They cannot move against each other, they cannot move away from each other, they cannot move towards each other, so the shape is fixed and the volume is fixed. In a liquid, the atoms are able to move relative to each other, but they are still connected and they are still sort of scrumped together. So the volume cannot change. You can't squish it because there's no gaps to squish it into, but the shape can change. And in a gas, the atoms are spread out, which is why they have lower density, and they're able to move around, they're able to be compressed, they're able to expand. They're in random motion with no bonds between them. So solids, liquids, and gases can be explained and easily explained using atomic theory. There's good evidence that atoms exist. Other evidence comes about because of this motion that you can see in the video here. This is called Brownian motion. You can see the little particles jiggling around. Now these little things are pollen grains. Pollen is the sex cells of plants, or one of the sex cells of plants. It's small, it's not actually alive. Now when Robert Brown looked at this in 1850, he could see them jiggling, but he had no explanation. Some people said it's because they were alive, or they could be alive, but that's not true. The same phenomena can be seen with smoke. If you take smoke from a cigarette or from a burning source and look at it under a powerful microscope, again you will see them jiggling around, and smoke particles certainly aren't alive. The man who developed the correct explanation was Einstein. Einstein realized that what was happening was that molecules of air or liquid in which our pollen or cigarette smoke is suspended are hitting the smoke particles or pollen particles all the time. Any individual one atom isn't going to make a difference, or particle isn't going to make a difference. But what happens is that you have several 100,000 hitting one side and slightly less hitting the other side. And that difference of, say, a few 100,000 atoms is enough to jiggle the object around. That was the only explanation that made sense, and so Einstein effectively, as far as you can do this, he effectively proved the existence of atoms because of Brownian motion. Another piece of evidence for the existence of atoms is the behavior of balloons. When we inflate a balloon, say using helium, it stays inflated. The rubber of a balloon or the plastic of a balloon wants to shrink it, but it can't. And it can't because the air molecules, in this case helium in this balloon, are rushing around, banging into the sides and keeping it inflated. The size of a balloon is a balance between the air particles inside banging on the inside of a balloon and the air particles outside banging on the outside of the balloon. In terms of energy, well, particles, especially if they're bonded together, can show both kinetic energy and potential energy. In this diagram, the top row shows the different forms of kinetic energy that particles can have. Translational motion means just moving around, side to side, forwards and backwards, up and down. That's obviously kinetic energy. In addition, if they have a particle that's bonded together, those bonds can rotate, which gives you rotational energy, and particles can vibrate, either fixed within their lattice or atoms within molecules vibrate. All of these are kinetic energy. There is also potential energy. On the left, you have intramolecular potential energy. So, molecular energy within molecules. That's basically atomic bonds as we would now understand it. And really, that's chemistry. In chemical reactions, those bonds are broken and reformed. Chemical reactions take place and they're endothermic or they're exothermic. That energy can be released or they need more energy. We're not going to really look very much at that in this unit. This, on the other hand, which is bonds between molecules, we will look at. In gases, there are no bonds, or certainly no appreciable bonds between molecules. But in solids and liquids, there are. In solids, it's these bonds between molecules which hold the atoms and the molecules in place, which makes it a solid. So that energy is present as potential energy. In liquids, the bonds are weaker, but they are still there, which is why liquid particles are able to move across each other, but are still squished in together. So overall, the internal energy of a substance is a combination of the kinetic energy and the potential energy, measured in joules. Temperature is related purely to the kinetic energy, and it's a measurement of the average kinetic energy possessed by the particles in that object. The average kinetic energy. That says nothing about the potential energies. But if the average kinetic energy is increased, then the internal energy will increase and the temperature will increase. The only time you have to really worry about these intermolecular potential energies is if you're changing state, if you're changing from solid to liquid or liquid to gas or some combination thereof. Then energy will have to be put into these bonds or taken out of their bonds. As long as the state or phase stays the same, then you just have to worry about kinetic energy. So a difference between philosophical atoms and real atoms. Philosophical atoms are divisible. They can be split and made from smaller components. And real atoms are divisible. They can be split, whereas philosophical atoms cannot be split. And they are mutable. They can change. Philosophical atoms could not change. So real atoms and philosophical atoms not really the same thing. Okay. Thank you very much.